Still, I think there's something missing. Even if we have a neural architecture which appears to predict time series very well, even if we have a variety of techniques for prediction, classification on the one hand, reasoning and rules on the other, the link between these is still missing. For example, if you're trying to predict how other players or pedestrians on the road will move, or if you're trying to predict the consequences of a decision, suppose one takes a decision, one imagines the future. If I did X, then Y will happen. If I did Z, then A will happen. And we continuously imagining the future by playing things out in our head. The missing element is that symbolic reasoning, optimization, planning, these features or these sort of techniques appear very different from the regressions or the neural learning or sequence prediction or naive Bayes classification, which is essentially data-driven predictions that we've seen. Reasoning requires one to learn rules, one requires one to learn classes, and then reason in a symbolic way about these things. And the link between how data-driven bottom-up techniques eventually give rise to higher-level symbolic reasoning in an architecture like the brain is a missing link. We still don't know how that happens. The hierarchical temporal memory promises that yes, we're going to learn about this, but that's not been demonstrated yet. So in the absence of that link being there, there are other ways to put these different techniques together in practical systems. The most popular one is called a Blackboard architecture, and it's a very old technique going back to the 50s and is now starting to get used increasingly in complex AI systems which need to use many different techniques, some bottom-up data-driven, some top-down symbolic reasoning oriented, and this is how the Blackboard architecture works. The Blackboard architecture consists of a blackboard where knowledge or that what one learns about the world is posted, and this knowledge is posted by knowledge sources. Now, knowledge sources can be of many types. They could be bottom-up feature learning, clustering, sequence miners like HTM, classifiers, so things which learn from the data directly. Or they could be symbolic rule engines or decision engines which do planning or reasoning. And they operate on a common blackboard. So the lower level data-driven knowledge sources might learn something about the world, like what are the features to look for, what are the classes, what are the rules, and then higher level rule engines might operate on these rules to perform reasoning, do planning, and take decisions. And a controller looks at the blackboard and tries to figure out, based on what is available on the blackboard, what kinds of knowledge sources would be most applicable to the kinds of stuff which are on the blackboard. So this is a way of putting different types of machine learning techniques, reasoning techniques together in one architecture. It's a hierarchical system, and some Blackboard systems are also Bayesian in the sense that if there are two different elements are on the blackboard, placing a third element might make the probability that one of the older elements, which was already deemed to be true, become less true through something like the explaining away effect. So those are called Bayesian blackboards. Some examples of blackboards are one of the earliest examples is speech recognition. The first speech recognition systems used blackboard reasoning. So the lower levels of the blackboard would detect things like phonemes, and then higher levels would detect words, and even higher levels would talk about sentences, and at each level one is not only going bottom up, but one is using the predictions at the higher layers to drive the reasoning at, or the classification at the lower layer. So the likelihood of the next word being a particular one is driven by what the previous word is, and that, as we've seen in a few lectures back, but that also drives what phonemes to look for. So lower level classifiers are adjusted based on what possible words are most likely in this particular higher level context. So that's how speech recognition systems have used this hierarchical reasoning fairly effectively. There are other systems which deal with analogical reasoning, which are essentially ways of trying to mimic analogy, like who is the Dhoni of USA. So how do you map different frames of reference to different contexts through analogies? I'd like to show you an example of an analogical reasoning system, or at least one that tries to mimic analogical reasoning. This one is due to a student of Hofstadter called Melanie Mitchell. Hofstadter, if you remember, was the author of the Pulitzer Prize-winning book Gödel, Escher, Bach, which many of you might have read. It's an old book, about more than 30 years old. Melanie Mitchell, his student, has recently written a book called Complexity, which is also a very interesting exposition of a variety of areas in artificial intelligence and complex systems. Well, let's look at what analogical systems reasoning works in the copycat program of Melanie Mitchell. The analogy one is trying to mimic is if you're given a transformation between ABC, which takes ABC to ABD, it's like a puzzle, what would you deem as the analogous transformation of IJK? Well, think about it. Let's see what the system does. It's reasoning. It's trying to find out what the analogy is between these two and apply that same analogy to this particular string. And it figures out that the analogy is replace the letter category of the rightmost letter by its successor. And it came up with IJL. Let's try it again. This time we'll give it a problem ABC goes to BBC and see what it comes up with. The Blackboard architecture is reasoning. It's different types of rules are being applied in a hierarchy, and each rule is affecting what to look at next. And it comes up with JJK, replace the category of the leftmost letter by its successor. It has learned the analogy. So as we can see, the Blackboard systems are extremely powerful, and they do form a way of marrying the bottom-up data-driven reasoning with the top-down symbolic reasoning, and allowing both of these to influence each other, just as Bayesian networks and hierarchical temporal memory all also include this element of top-down, bottom-up reasoning working together. So we will now end the course with a recap. I hope you've enjoyed this lecture. I've tried to cover many exciting things, at least things which I find extremely exciting and promising. A few things in a bit of detail, like linear regression and the ability to predict values using regression, and maybe even other techniques like logistic and SVM if you use packages. And then some more speculative AI aspects and how they come together for big data analytics.